All right. Hey, AP Chemistry. So I got some requests to talk through our Unit 1, Part 3 notes on the different trends. This is going to be very important for the AP exam, so make sure you understand or can get through this. So one of the first things we talked about was atomic radii. If you could remember the trend, if you're pretty good at memorizing, I would remember the trend. Atoms get larger as you go over to the left and down a group. So it gets larger as you go from right to left, and then it gets larger as you go to the bottom of a group. And that's what we have the trend there. Now, I also briefly talked about why this happens, and this is because Z effective, and I put some information here. So if I have a stronger Z effective, which means the nucleus has a greater charge, or I have electrons that are feeling a greater charge, the atom is going to be smaller, and that's what it says right here. As you move to the right across a row in the periodic table, the effective nuclear charge experienced by the electrons in the outermost shell increases, resulting in stronger attractions between the outermost shell and a smaller radii. But the opposite happens as you go to the left. As you go to the left, or going from right to left in a row, the Z effective is decreasing. So the atom is getting bigger because those electrons are not being held tightly. The same could be said as you go down a group. As you go down a group, you could notice that it's larger. Well, it's larger because there are more electrons. And as you can see, as you move down a column in the periodic table, the number of shells increases, resulting in larger orbitals and larger atomic radii. What this means is I have more electrons that are building up around my atom. It's shielding the nucleus, and so the nuclear charge is becoming smaller. And so those electrons are not as held closer or tighter to the atom, and so the atom ends up being larger. And so that's why I put a star here with more electrons. So if you look like something at cesium, cesium has a really large size because it has a lot more electrons, and all those electrons are really covering up and blocking the nucleus, shielding that nuclear charge. So two effects there. So for atomic size, make sure you know, because you're going to have to apply this later, as you saw in Unit 2, that as you go down a group, the atom gets bigger, and as you go to the left, the atom is bigger, or as you go to the right, the atoms get smaller. Okay? I'm going to skip talking about ions and writing electron configuration for ions, because we talked about that in another set of notes. I want to talk about ionic radii. Same idea. Thinking about effective nuclear charge, if I ever wanted to say why. But in general, look what I have highlighted at the top. Metals and metalloids tend to lose electrons when they form ions. Metals and metalloids are on the left side of the periodic table. When they form an ion, they end up smaller in size than their neutral atom. When I say neutral atom, I mean it hasn't gained or lost electrons. If I go back on top here, these are my neutral atoms. These are all my atoms neutral as their size. These are my ionic atoms. These are their ion sizes. So metals tend to lose electrons. They will end up being smaller than their neutral atom. Non-metals tend to gain electrons and will be larger. They get more electrons, they become bigger. They also get more electrons because all the electrons start pushing away from each other and the atom becomes larger. What you need to understand is that in general, for the size, a negative ion will be larger than a neutral atom, which will be larger than a positive ion. Know that. Just think, if I'm negative ion, I've gained electrons, I become bigger. If I'm a positive ion, I've lost electrons, I become smaller. Okay? Now, there is a weird thing that happened, and we were talking about Coulomb's law, and we talked about this very briefly in Unit 2. But look at what happens to the metals. Look at sodium and magnesium. Sodium ends up being larger than magnesium. And this only really happens with the metals, especially these group 1 and group 2 metals. For metals, this weird thing is happening. As I'm losing electrons, I am getting rid of those electron repulsions, And I have electrons that are going to be closer now to the nucleus. If you look at sodium and magnesium 2 plus, they have the same number of electrons. Sodium originally has 11 electrons, but as a sodium ion, it has 10 electrons. Magnesium ion usually has 12 electrons, but as Mg2 plus, it also will have 10 electrons. Between sodium ion and magnesium ion, they both have 10 electrons. But why would the 10 electrons of magnesium be closer than the 10 electrons of sodium? That is because, why? Effective nuclear charge. Magnesium definitely has a stronger effective nuclear charge, so it's going to be smaller in size than sodium. That is not going to be a typical trend that you have to remember. You'll probably be given information on a quiz or the AP exam. It'll say something like, oh, sodium plus 1 has 10 electrons, but it's found to be larger than magnesium, which also 2 plus, which also has 10 electrons. Why? So they have to give you information on the AP exam in order for you to explain why. So in general, remember that negative ions are going to be larger than neutral atoms, which are going to be larger than the positive ion of an element. Okay? Now, this whole business of why with Z effective and where electrons are going and coming and taking or leaving is because of electronegativity. And now we talked about electronegativity in a POGL that we did recently for types of bonds. Remember the trend for electronegativity. I highlighted fluorine for a reason. That's the F right here. Fluorine is the most electronegative element. All elements have smaller electronegativities compared to fluorine. And a nice thing to remember is the closer you are to fluorine, the more electronegative you're going to be. So aluminum versus magnesium, aluminum is closer to fluorine than magnesium, it's going to be more electronegative. Silicon versus cesium, silicon is closer to fluorine than cesium, it's going to be more electronegative. Now, on a quiz, test, or exam, something like oxygen and chlorine, I'd have to give you their electronegativity values in order for you to compare anything. As you could see on this table, oxygen has 3.5 and chlorine has 3.0, so you could see that oxygen is more electronegative than chlorine. I'd have to give you information. If you had to explain why, you'd probably say something about Z effective. If ever a question it is asked, why do we see a certain trend? It has to do with something about subatomic structure, nuclear charge, attraction of electrons for an atom, all that. So electronegativity talks about this attraction an element has for electrons. Fluorine really wants electrons. Francium or cesium or radium, they don't care about electrons. So they have low electronegativities. Okay, metals tend to give up electrons because they have low electronegativities. Non-metals tend to want electrons because they have high electronegativities. And we talked about that in our POGL. All right, the last two trends I'll talk about are ionization energy and electron affinity. So for ionization energy, it is the amount of energy it takes to remove an electron from an atom. That's positive energy. I want to remove that energy. It requires energy. It's endothermic, it's positive. And remember the schematic. Energy plus X, which is an atom, ends up being X plus electron. This is X is like a neutral atom or a neutral element. I'm adding energy to it to remove an electron. It becomes a positive ion, and an electron is ejected and leaves. For the trend in ionization energy increases as you go to the right, and it decreases as you go down. Why does this happen? Coulomb's law, or Z effective. So fluorine, as we set up here, fluorine is the most electronegative element. It really wants to hold on to electrons. It does not want to give up electrons. And as we said all the way up here too, fluorine is probably going to be among the smallest atoms. Ignoring the noble gases on the right, fluorine is among the smallest with electrons because it has a very high nuclear charge with respect to electrons in a shell. So fluorine is among the smallest. Fluorine is the most electronegative. And because of that, it does not want to give up electrons. Now, look at the noble gases, especially like helium, neon, argon, krypton, xenon, radon. They have crazy high electronegativities. And we're going to talk more about that when we talk about the octet rule. But noble gases have full valence shells. They do not want electrons, nor would they want to give up them. So their energies tend to be among the highest. They have full electrons in their shells. If I write their electron configurations, it is full amount. So 1s2, 2s2, 2p6, 3s2, 3p6, right? All full. Fluorine does not have a full octet, doesn't have 8 in its shell. It would be 2s2, 2p5, and it needs and really wants one more. And if it just wants to take one more, you don't want to give up one more for fluorine. So again, because of that, fluorine has a really high ionization energy because it does not want to give up electrons. But then our metals, as we recognized before, metals are low in electronegativities. Our metals do not care about their electrons. So it will easily give up its electrons. So the amount of energy it takes to remove an electron from a metal is quite small because they don't care about holding on to them. So for ionization energy, as you go from the left to the right in a row, it increases. As you go down, ionization energy decreases. And this is because of Coulomb's law and effective nuclear charge. The last thing I will talk about is electron affinity. It is the exact opposite type of schematic than ionization energy. For electron affinity is defined as a change in energy of a neutral atom when an electron is added. Ionization energy, an electron is removed. For electron affinity, energy is added. And so here's the schematic. X plus, which is my ion, or it even could be my neutral atom, plus an electron, and I get the neutral atom plus energy. Or it could be a neutral atom plus an electron, and I get X minus plus energy. X could be an element or an ion. I know in the definition it says of a neutral atom, it could be of the ion, or it could be of the neutral atom. Let's focus more on for electron affinity schematics for the neutral atom. So I was just trying to draw the backwards version of ionization energy because it is. So electron affinity is the amount of energy that is released when an electron is added to an atom. Notice how I said it's released. Exothermic, negative. Okay, so when I give an element an electron, it releases energy. It's kind of like when we make a bond, as we mentioned later. So if I put two things together, like two atoms or an electron and an element, energy is released. Now, thinking about this negative value, and I specified this as increasing negatively, it's kind of like the exact same trend in ionization energy. Fluorine really wants that electron. When you give it that electron, it's going to release a lot of energy. Or think of it as money, and that was the analogy that I made in class. Fluorine will pay anything to get that electron. It will pay tons of joules of energy to get that electron. So electron affinity energy increases negatively as you go to the right, and it decreases negatively as you go down a group. So metals or elements that are lower in a group are like, I don't care about electrons, don't give them to me, I'm not going to pay, or I'm not going to give up that much energy. Non-metals or things closer to fluorine really want electrons. They will give up a lot of energy and pay energy for them. So remember that trend for electron affinity. Metals, left side, do not want electrons, so they're not going to give up. They're not going to really give up too much energy. The negative energy that is released is going to be small. For non-metals or elements that are closer to fluorine, they're going to release a lot of energy. And here's the note here. More energy released, the greater the attraction for electrons. How do we know trend in attraction for electron? Again, everything goes back to electronegativity. Fluorine is the most electronegative element, so it's going to release the most amount of energy when it gets an electron. Francium is the least electronegative element. It's going to release the smallest amount of energy if it gains an electron. All right, so this is me going through the last trends in our Unit 1 notes. Hopefully this video was helpful in kind of going through the notes again. If you would like or need more examples or questions, we will work on them in class, or simply message me in the Remind for more examples or other things to understand